All right, so this is just going to kind of go over the Desmos that we did. There was a problem set that I asked you guys to try first, and then we discussed it in class. So I'm just going to go over that for those who missed class for whatever reason. A couple things that I covered right before we got started was clarifying stuff about degrees. So the degrees is just the number of edges connecting to a node. So in this graph over here, these are two separate graphs. A has a degree of 2 because there's 2 edges coming off of it. Similarly, B is 2. Each of these have a degree of 1 because there is just 1 edge coming off of that, whereas C has a degree of 1, 2, 3, 4, and 5. So C is a degree 5. If you have a loop like this, even though it is a single edge, it is connecting 1, 2, 3, 4 times, and you can almost think about it as like, think about the neighborhood. And when I say the neighborhood is like zoom in on the point, how many edges appear to be coming off. You can't really tell that this pink will continue all the way around and come back over here for a variety of reasons. And again, as with anything in math, you could make some arguments for or against, especially when it's a definition. But in this case, what we're going to call this is we're going to say that a loop counts as 2. So this is a degree of 4. Okay. Also going to be useful later is making sure we know what a connected graph versus an unconnected graph. So let's say that these are B, A, C, D, E, whatever. They're similar graphs, doesn't matter. This is connected because I can get from any point to another point, any node. Here, there's no way for me to go from A to E or from B to D or C to A. And there's like this gap that's happening here. So this, although together it is a connected, or it is a graph, it is an unconnected graph because we're missing some connections there. Okay, and we're also going to need adjacency tables. If you recall, we set them up kind of like this, and the question is, how many times does A connect to itself? There are no loops here, so I would either leave this blank or put a 0 there. It does connect to B. It connects to C twice, and it does not connect to D. B is connected to A only the one time. It is not connected to C directly. Obviously, you can walk to C, but it is not connected to C, and it is not connected to itself. There are no loops. It is connected to D twice. Continue on, and you will end up with this table here. So this is the official adjacency table for this. And important to note is we can turn this into a matrix if we literally just kind of grab all of those same, wow, how did I just get some of them? Oh, there we go. Grab all of those points, and now it's a matrix. Woo, we put the brackets around it. It's a 4x4 matrix. We're going to need that in a little bit. Okay, but what happens if you have a directed graph? The only difference between this pink graph and this one is that now I have arrows. It's going to be very similar, but a little bit different. The biggest difference is that you're going to label either the top or the bottom as to or from, and I think that it probably makes sense to make this to and this say from. So for example, right here, this spot, I'm going to highlight right there, that would be if I am moving from A to C. So does that happen right there? So from A to C. Oh, yes, it does. There is one single connection that would get me there. So I'm going to have a 1 there. If, however, I was looking at maybe this spot right here, B from B to A, that doesn't exist. The arrow is going in the other direction. It wants me to travel this way. So that does not exist, and it is a 0. That is different, of course, than what we had over here where we did have a connection because there just was an edge going between them. So you're going to go through, so maybe pause the video real quick and see if you can fill this out, and then I will pause my recording, and in about a second, you can see it. Okay, so now we have this directed, oh goodness, wrong button. Directed graph here. Which you'll notice is not the same as here because obviously these arrows are changing things. Okay, now we're on to the Desmos activity. You were given a bunch of problems and your goal is to just look at them. You can then construct in this Desmos area. Now I'm just doing this on my iPad program, so I will just be writing things. But you're welcome to draw stuff over here. So is there a graph on 6 nodes with degrees 2, 3, 3, 3, 3, 3? I should say, please try all of these before you watch this video because I'm just going to go through the answers. In this case, is there such a graph? No, there is not such a graph. And the reason for that is that if you add up all of those degrees, so you got your 2 plus 5 times 3, you're going to get 17. And the sum of all of the nodes when you have a graph is going to be even no matter what you do. Let's look through why. So let's say I had my 6 nodes here. The sum of all of the edges or the degrees right now is 0 because there are no anything. If I add one edge, right now, so now I've got one edge. The degree sum is 2 because I've got a 1 and a 1. If I add another edge, doesn't matter where, now I've got 2 edges, the degree sum is 4. Every edge, because it starts somewhere and it ends somewhere, is going to add 2 to the degrees, so it is not possible for the degree sums to be odd. Can a degree be odd? Of course it is. This degree is 1. You could very easily have a degree of 3 now. But the sum of all of them, we'd have a 3 plus a 1, 1, 1, 1, 1. 3 plus 5 would get you 8. So no, it's not possible to do something like this. So what about a 6-node graph with these degrees? Again, if you sum them, you're going to find the same thing, right? 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10, and 10 plus 5 is 15. It's not going to work. It's also kind of interesting though, and it might be worth spending some time. I hope you did this as you were going through it, trying to sketch out what this would look like. You would have to, at least for the 5, and this came up in class. One person said, well, if this is a degree 5, then it would have to go 1, 2, 3, 4, 5. It's not possible to have your degree 0. I thought that was kind of clever, but then somebody who is smarter than me, just kidding, somebody who's thinking more, it's not about who's smarter or less smart, it's just the ideas that we've had, brought up that this person could have like 2, 3, 4, 5, leaving open the possibility of zeros. But the odd degree sum makes this not possible. So is this one possible? Nope, sure not. 4 nodes with degree 1, 1, 2, and 2 sure is possible. There's lots of possibilities. In general, if you even just have them in a nice straight line, this will work for you because this one is degree 1, this is a 2, this is a 2, and this is a 1. And there are a lot of variations on that. People wrote Z's or people wrote U's, literally just kind of whipping this chord around. The other possibility, which I like myself, is if you have 2 of them connected like that, and then you have 2 that have loops, because each of these would have a degree of 2, and these would each have a degree of 1. So this one's possible. Okay, then this one brought a whole bunch of confusion. And I think that I might have counted the wrong number here. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Shoot. There should only be 10 of those. But 10 nodes with degree 1, easily done if you simply make 5 pairs like this. And lots of people were like, okay, well then there's one way to do it because I can't think of anything else. But it's different if you name them, right? Now A and B are paired together. So this is different if A and B are paired together than if A and C or A and D or A and E are paired together. So the question is, how many different pairings do you end up with? We had a lot of people who thought this might be 10 factorial, but that is way too big. And I would encourage you to start thinking about, okay, what does 10 factorial mean? Well, 10 factorial is literally like 10 times 9 times 8, etc., etc. The classic example of what this is is literally if you took all 10 of these dots and lined them up in a row. How many ways could you line up 10 people? And there's a lot of ways that you could do that, but that's not what we're doing in this case. So think about it perhaps like this. We don't care about the order that they pick people, we just care about how many pairs there actually are. So if we start with A and we say, hey, A, look around, pick a partner. A has 9 different people to choose from. Then A picks some random partner. Okay. The next person, and it doesn't again matter who we pick in this case because the order doesn't matter. It's just what the pairs are in the end. It's not like the first pair, the second pair, the third pair. This person now has how many people to choose from? 1, 2, 3, 4, 5, 6, 7. I think I skipped 8. 1, 2, 3, 4, 5, 6, 7. Yep, they have 7. Whew, thought for a second that things had gone terribly wrong. Next person has 1, 2, 3, 4, 5 people to choose from. Next person has 3 to choose from. And the last person has just 1 person to choose from. This is going to be your solution. Please do spend some time thinking about all of these, but I will tell you, and by all means ask as many questions as you need to, that all 3 are correct. So if there's an odd number of nodes, then it has a node with even degree. Has to happen because it has to happen. It has to happen because, like, if you have an odd number of nodes, either they're all 0, or as soon as I start connecting, now I've got 2 that are odd, and then the 0, we're just going to consider even here, would be 1. You can play around with it, but it is true. It has an odd number of nodes, then the number of nodes with an even degree is odd, and then the sum of all of the degrees is twice the number of edges. Play around with all 3 of them, but all 3 of them are true. And then there was this one. Whew, quite the doozy. And sorry that I got caught off here, so just imagine that that's got a C right there. This is the statement that you're trying to prove. Prove that either G or its complement are connected. So the complement of any graph is essentially its opposite. All of the nodes are the same, but the edges are not. Any edges that exist in G do not exist in the complement of G. So here, A and B are connected. Here, A and B are not directly connected. B and C are not directly connected. Here they are. So this is like G, and this is the complement of G. If you were to take these and put them on top of each other, you would get a complete graph. That means that every node is connected to all other nodes. So what your job is to do is prove that either G or G complement is connected. Spend some time trying that first and then come back here. I'll just keep going, but pause. One of the ways is to do this with actually cases. So this is what we call a proof by cases. Okay, so here is the proof. First of all, you could either say G is connected, and then you're good. You don't even have to check G, because you're either going to say either G or not G. The complement of G is connected. In the second case, you're looking at a graph where G is not connected. To illustrate this, I'm going to just kind of draw a G over here that is not connected. Okay, so G is not connected. We have at least one subgraph here. I'm going to call this my S1. And this is going to be my S2. That is not connected. You could imagine that there are more. Well, the complement, what's going to happen is that A, which is part of S1, is going to connect to every node in S2. So it's connect here, and it's going to connect here. B is also going to do the same thing, and so is C. And in fact, in this case, we're actually also going to get a connection between A and C because we didn't have that before. And now we already also have that E and D have connected to everything. And voila, thus the 2 subgraphs are connected And I know that I should still be able to walk between any of these nodes because all of those nodes are going to be connected to all of the ones over here. So I can still get from A to C, or A to B, or B to C, etc. And thus all of the nodes are going to be connected. And obviously if there's more than two subgraphs that are disconnected, then this will work because they will also reach out and connect to those as well. Let me know if you have questions. The last thing that we started on whatever day that was, Friday, was this investigation, which is in your book. We will finish this on Tuesday. But what they ask you to do is, for this graph, find the number of walks of the given length between the two vertices. So the length just means you've crossed one edge. All of these edges count as one unit. So between A and C that are length 2. Well, if I am a dude, I start here, I could go over here and down here, that's length 2. If I just go directly to C and go away, that's length 2, so it's not going to work. So the only way is that edge right there. So if I go A, B, C. So there is exactly one walk there. Length 2 between C and C. Well, if I start here at C, I could go up to A and back, up to B and back, up to D and back. So there are 3 walks between C and C that are length 2. Length 3 between A and C. This one is a bit harder to count, so I'm gonna move that out of the way, I guess. What we could do between A and C length 3, we could go 1, 2, 3, so that will work. That's AC, DC. We could also go A, B, A, C. We could also go A, C, B, C. And finally, we can just toggle back and forth and go A, C, A, C. So there are 4 walks there. Length 3 between D and D, there are none, because if I go here, that's 1, 2, 3, I can't get back. There's no way for me to get back. And if I did 1, 2, 3, I can't get back. So there is a total of 0 here. So then it asks you to find the adjacency matrix for this graph. I have that here, right? A is not connected to A, but A is connected to B, etc. And then it asks for the m squared and m cubed. So if this right here is m, and in fact, I have just taken this matrix and rewritten it over here. Here's m squared and here is m cubed. And what I want you to notice is this. Length 2 between A and C. Well, length 2, I'm going to start looking at m squared, and if we have A, B, C, D, A, B, C, D, notice that between A and C, both ways, we end up getting 1 walk. Between C and C, wrong tool, my bad, wrong color, there we go. Between C and C, we're going to get 3 walks. If we're going to deal with length 3 between A and C, we should get a 4. So between A and C here, oh, check it out, we got a 4 there, we got a 4 there. And length 3 between D and D, we should get 0. Check it out, we get a 0. And in fact, you could extend this out. We did this in class. This is m to the 7th. And like this right here, this 14 is 14 paths of length 7 between D and itself. So if you started at D, you could go away and come back to get a length of 7, and there's 14 different ways to do that. We will pick the rest of this up on Tuesday. Let me know if you have any questions.